the third construction we loosely called the intersection tori, although it's really a whole series of ideas around this illustrated by it, intersection tori. And essentially what we're trying to construct for four manifolds is a model of a double point. So the problem with four manifolds is that generically disks are only immersed rather than embedded, and what you can end up have is you have points where your disk intersects itself. So you have two surfaces, two-dimensional surfaces intersecting in a four manifold in an isolated point. Now the model that I am going to construct has the following properties. Well, your two, so again I'm halving the size of the dimension to be able to picture it here. So here you have some disk D1. In fact, this is a Lagrangian disk with respect to a natural symplectic structure. On the other hand, your second disk, so another Lagrangian disk, D2. No, sorry, D2. And suppose they have an isolated intersection point here. Now what we can do is to look at the regular normal neighborhood of these and look at the boundary of that. So you look at a kind of a strip around each one of those, and then you look at the boundary. So here we take the boundary of the normal neighborhood of the first disk. And in fact, what we're going to show is we can do that so that that boundary is null. Similarly, for the other disk, you end up with, this is the boundary of the normal neighborhood of the second disk. And again, this is going to be null. And then finally, these two normal neighborhoods, boundaries of normal neighborhoods, intersect in, well, the picture here is 4 points, which is S0 cross S0, because I'm drawing it all one dimension lower than actually what I'm working with. But in fact, these points here, in fact, represent an S1 cross S1. It's a two torus, and this is the intersection torus that I've just mentioned. So this is the intersection torus, and in the picture that I'm drawing here, the cores are Lagrangian, the boundaries here are null, and these intersection tori turn out to be totally real, and in fact Lorentz with respect to this neutral metric that we have. Okay, so this is the model I want to try and construct with these geometric properties around this isolated intersection between these two disks. And the way in which we're going to construct it is as follows. So I'm going to do it all in R3, right? But I'm not particularly concerned about that. As we've seen, a lot of this stuff goes through into any three-dimensional space of constant curvature. And what I want to think of is if you take, say, a convex surface in R3, and you take another convex surface, say down here, and you look at the oriented normal lines to this surface. Well, the oriented normals, there we go. But if you notice the way I've drawn it here, if you continue down here, this is also the oriented normal to that, say at that point. And the other ones miss, they miss each other there. So what you have here is the oriented normals in a neighborhood here are distinct for these two surfaces. So you could call that, if you want, you can just call that D1 and that D2 if you like. And you can see that they're intersecting, the oriented normals are intersecting precisely at this one normal, this common normal. Okay, so with that, we want next to look at how will we construct a regular normal neighborhood, right? So we have this normal neighborhood of each one of these disks. So as we said over in L of R3, so in the space of oriented geodesics of R3, these just look like disks that are intersecting somehow. Yeah, it's kind of hard to draw, of course, which are intersecting just in a single point. Now, what we want to do is build up some normal neighborhood around them. So to build up a normal neighborhood, one thing you could do is just take your normal here and just rotate it so it's not exactly perpendicular. In fact, what we do is we go all the way down till we get exactly the tangents. And so in our model, the regular normal neighborhood, so this normal neighborhood of your disk is exactly the same as the hypersurface of tangent lines to that disk. So this is where this null surface comes in here, how we know the boundary of this normal neighborhood is null. It's exactly the hypersurface that we had studied in the earlier part. Now, So here we have these Lagrangian disks, the Lagrangian because they're perpendicular to lines. Then we have these normal neighborhoods. The boundaries of these normal neighborhoods are precisely these hypersurfaces that we constructed in the second section. And now we want to know, what about the intersection of the two normal neighborhoods, the boundaries of the normal neighborhoods? Okay, and so the claim is, well, let's just assume, again, we go into the more detail in the paper in the different cases, but let's just assume that if you take, let's take S1, which is a round sphere, and S2 is a round sphere, again, two of different radii or same radii, it doesn't matter. And let's assume that these two surfaces do not intersect. So the intersection is 0. And in fact, I don't want one sphere to be inside the other either, so we better throw that away. So essentially what we're looking at is a sphere, and maybe draw a smaller sphere here. Okay, now I'll draw a bit more details in a second on that. Now what we're interested in is the hypersurface associated with S1 and its intersection with the hypersurface associated with S2. There's S1, there's S2. So again, let's think about that. This is a tangent vector. We want something that's tangent to S1 and tangent to S2. Now when we look at this here, it's not too hard to see, well, what kind of vectors are we looking at, what kind of lines are we looking at? Well, there's one line. Allow me to have that tangent there and there. So there's a common tangent. Now, you may notice that you can flip the orientation, so in fact we're going to get two copies. So actually everything is actually doubled, but let's not worry too much about that. And then after we've done that, we think, well, hang on a second, here's a little bit more. What about one that crosses this way? So it kind of hits here and hits here. And again, the other orientation either. And then finally, we could also do this from here. Sorry, I'm supposed to touch it at the side. Okay, so when we do that, then you can see it looks like there's two different classes. There's the ones kind of inside and the one outside. And remember, of course, we can rotate around their common axis. So we can rotate, we have a kind of an S1 worth when we rotate all that around. However, what's missing in between those two is the following. If you take, say, where this intersects and where this intersects and where this intersects and this intersects, and the same thing over here, suppose that intersects there to there, and say this one intersects there to there, in between here and here, it's not immediately clear, but if you take a point here, so every point here has one line tangent, common tangent. Every point here has one line tangent. Here it has none. And in here, it turns out to be 2. And the same thing here. So there's none of the tangent lines here are tangent here. On this blue line, there's exactly one that's tangent to both. On this line, there's one that's tangent to both, and none on that side again. And in here, there are 2. So how do you see those 2? Okay, it's a little bit tricky to see, but then once we've seen that, we'll see why this ultimately is a torus. So again, let me draw that again. I'll draw maybe this one here and this one here. And what I want to look at is move down a little bit off the symmetry, and take a point there, and take the tangent plane through that point. So let's take that tangent plane. Suppose it comes down like this. Well, it's going to intersect this. Where is it? Well, it's tilted down, so maybe it's going to intersect at something like around here. It's not going to be a great circle or anything. And where is the common tangent? Well, the common tangent here is the one that goes from here to here, and the one that goes from here to here on the other side. So there's 2 common tangents to that point. And these are exactly the points in between. So this is 0, 1, 2, 1, and 0 again. And the same on the other side. So what you're seeing here as you come across, you have an S1 going around that way. You have here, you have one tangent line that's common. Here you get 2, and they kind of separate out, then they come back together again. You've got 2, and then they get closer together again. And then when you hit to here, they go to 1. So here you can see you have a circle. You have a point, 2 answers. So you have an S1 here, and then you also have this S1 here. So the intersection that you get is a torus. Now again, with the orientation, you can flip the orientation the other way, and so what we find is in the situation that we just looked at, intersect H of S2 is actually 2 disjoint tori. Again, the 2 just comes from flipping the orientation. So again, this is when the two don't intersect. It turns out then when you do this in specific detail and compute this, this T2 turns out to be totally real. So that means it has no complex points on it. And it's also Lorentz. The metric on this torus is, in fact, signature 1, 1, and it's not degenerate. So it's totally real Lorentz tori, is each one of these are. I guess one other way we could look at this is if you think of this as a planet and say that is the moon. Well, here you're standing on this planet and suppose you're looking this direction. What is it that you see? Well, there's three different, when you're at this point here, there's your horizon. So here, this would be your horizon, because that's the plane that you're looking at off the tangent to the Earth, if you like to think of it as the Earth. So that's your horizon. So here's your horizon. And when you're at this point here, here is the moon. It's just touching. When it comes above the horizon, that's when you get your two intersection points. That's your gamma 1 and gamma 2, for example, if you want to call that gamma 1 and that gamma 2. And then when it goes above, you're back to 0. So that's 0, 1, 2, 1, 0. So that's 1 as the moon comes above the horizon, as you walk towards it, assuming that nothing else is changing, you're just starting here and walking from here to here, you'll see the moon coming above the horizon and the points at which it's intersecting the horizon, starting with 1, going to 2, reducing to 1, and then to 0. Well, they're exactly the points where these are exactly the oriented tangent lines that are tangent to both hypersurfaces. Okay, so with that then, why would be interested in looking at these intersection points? Well, the standard approach to four-manifold topology, one very important construction are Casson handles. Now, Casson handles try and deal with the problem of double points on a disk, and the normal picture you'd associate it, you have some four-manifold and you have a disk, but the problem is when you immerse the disk, it can have a double point. And because it has a double point, you want to try and get rid of that double point so you have an embedded disk, but the difficulty, as I say, is that you don't know that it may have these double points. Now what you can do is thicken it up, and then, thicken it up there, and then you can attach another disk to try and kill it. Now when you do that, again, this may have another double point. You can't get rid of the possibility that there might be another double point. And again, Casson's idea was to continue doing this and continue doing this, and every time you try to cancel this double point, you may introduce new double points. But in this iterative process, as you go to infinity, eventually what you get, the object that you get, is homotopic rel boundary to a standard open two-handle, D2 cross R2. The difficulty with this is that while it works in the homotopy category, it doesn't work in, for example, the smooth category. So we know that by work of Donaldson that these cannot be diffeomorphic to ordinary two handles in many circumstances. So you know these Casson handles, they have the right homotopy properties, but actually they're not exactly what you need to work in the smooth category. The idea that of much of the work that I've put here before you is to try and develop further some ideas about taking this construction and at each stage controlling in some way the boundary behaves using a neutral metric. So what I'm proposing, and these are the first baby steps, if you like, of that, is that we have a kind of a neutral Casson handle in which we try and extract some control at the boundary using this neutral metric with the null boundary and all the properties that we've just laid out before you. Okay, so much of this is aspirational, but you can see the direction it's going. The proofs are in the paper, and I hope this has explained it for you. Thanks a lot.